Today's presentation will be on some problems related to excess rainfall hyetograph and direct runoff hydrograph. So, as all of you know, that direct runoff hydrograph is a hydrograph minus base flow, and if you multiply area with this effective rainfall hyetograph or excess rainfall hyetograph, then you will get DRH, direct runoff hydrograph. Now this effective rainfall hyetograph is nothing but total rainfall hyetograph minus the initial loss and infiltration losses. Okay, so this is actually the effective rainfall hyetograph. And I think all of you know, or I will assume that you know what is hyetograph and hydrograph is. Hyetograph is rainfall intensity by time or duration, and hydrograph is discharge with or discharge versus time. Time is duration of the event for which that discharge is taking place. So the discharge or rainfall intensity is always placed in ordinate, that means y-axis, and the duration or time is placed in the x-axis. So in this presentation we will solve one problem on excess or effective rainfall hyetograph and direct runoff hydrograph. So the problem is like this: rainfall of magnitude 3.8 centimeter and 2.8 centimeter occurring on two consecutive storms, that means one after the other, for 4-hour duration each. That means one storm of 4-hour duration. One storm is of 3.8 centimeter and another storm is of 2.8 centimeter. Now this cumulative rainfall has generated a hydrograph whose data is given here. So that time from the first row is representing time from start of rainfall, that is when the rainfall started, and second row is representing the runoff from that rainfall. So as you can see, each column is of 6-hour duration, and the runoff actually starts from the second column when there is a flow of 5 cubic meter per second. So due to this column, we understood that there is some base flow component mixed in the hydrograph. So what we will do is we will first try to draw the hydrograph. I am not drawing as per scale or like that. So in this y-axis there will be our Q or discharge in meter cube per second, and this will be your time in the x-axis, which will be in 6-hour frequency. That means the first one will be at 0th hour, Next one will be on 6, then 12, then 18, then 24, and so on. So our job is to calculate the rainfall excess. You see, calculate the rainfall excess and the phi index. Okay, so let us see how to solve it. So as I have already discussed with you, excess or effective rainfall, this excess is also known as effective rainfall. When deducted from total rainfall, it will give you the initial and infiltration losses. And if you divide initial loss by the duration of hydrograph generated from that rainfall, you will get phi index. Okay, so the total duration of our rainfalls are, you remember, 2 rainfall of 4 hours each. So 4 plus 4 hours will be 8 hours. And initial loss we have to calculate by deducting excess rainfall from total rainfall. We know what is total rainfall. Total rainfall is already given, and it is like 3.8 plus 2.8 centimeters, so it is coming as 3.8 plus 2.8 centimeters, so it is coming as 6.6 centimeters. Correct? So total rainfall we know. We have to find out excess rainfall or effective rainfall. And duration of the hydrograph generated from this 6.6 centimeter total rainfall is 8 hours. It is given in the problem. 4 hours plus 4 hours. So after we get the effective rainfall, we will deduct that effective rainfall from total rainfall, and we'll find this initial loss. We'll then divide this initial loss by the duration of hydrograph to get the phi index. So the problem that I have discussed, or question that I have discussed in the previous slide, it asks you to calculate effective rainfall and phi index. So to solve this problem, you need to know about base flow separation technique. There is a video of mine in the YouTube. You can just search. You can go through that video first and then come back to this problem. And you have to know how you can calculate the area of DRH, or direct runoff hydrograph, and then corresponding to that the runoff volume calculation from a hydrograph, and also runoff depth calculation. Now you know this depth and volume can be converted easily. You know that if you divide volume, say volume represented by meter cube, and you divide it by area of watershed, let it be by meter square, so it will give you the depth. So all the climatological and hydrological terms can be represented by volume or by depth. But remember, if you are representing those terms in volume, you maintain that way. Again, if you are representing the climatological and hydrological parameters in terms of depth, then maintain that way from the starting to end of the problem. Otherwise, you will be confused, and often this is the reason why students make mistakes at the time of final calculation. Okay. So now let us see how we can find this effective rainfall. Okay. So first step will be base flow separation, as I have discussed, by straight line method. So from the graph itself, I have seen that there is a base flow component. So generally the base flow separation technique can be conducted by three methods. One of them is straight line method. The straight line method says that just join the beginning of point of hydrograph with the finishing point of the hydrograph by a straight line. Now I cannot, yeah, this will be a straight line. Now you will find if you observe all the ordinates of the hydrograph, the beginning point of hydrograph has a value of 5 cubic meter per second. And also at the end of the hydrograph, the same ordinate was observed, 5 cubic meter per second. So we assume that 5 cubic meter per second to be the base flow. And in the first step itself, you deduct this base flow from all the values of runoff you have. Okay, and you can get the values of runoff from the columns of that table that I have shown you in the first slide. Okay, so this will be your first step. Now second step is that, remember, you have to convert the runoff either into volume or into depth. So as rainfall is in depth and most of the calculation will be based on rainfall, we will convert, first we will convert the DRH into from discharge in meter cube per second to volume, that is meter cube. Okay, so to do that, you have to multiply 60 into 60 with 6 hours, because we have a hydrograph which have a 6-hour period or 6-hour frequency. That means the ordinates that is given has a frequency of 6 hours. So first convert this 6 hour into its second value. So first multiply 60, 1 hour 60 minutes. So 6 hour into 60 means 360 minutes. Then again you convert 60 to make it second. So 3600 second it will be. Why I am converting it to second? Because discharge is given in meter cube per second. If it is given in meter cube per minute, I could have multiplied only once. That means 6 into 60. But as it is given in second, I have to multiply 60 twice with this 6 hour. And if this discharge is given in meter cube per hour, then it is very good. We do not have to convert at all. No multiplication required. Keep as it is. Okay. So as the discharges are given in meter cube per second, if you observe the first table of the first slide, you will find that all the discharges are given in meter cube per second. So I have to convert the frequency of the hydrograph from hour to second. Okay. So by frequency of the hydrograph means, as you can see, all the values of ordinates of the hydrograph is coming at 6 hourly duration. Okay. Now let us see how to calculate the area of DRH. And as you know, whenever I am deducting base flow from runoff hydrograph, I have already mentioned this, I am getting direct runoff hydrograph. And okay, so, and remember that when you multiply effective rainfall hyetograph with the area of the catchment, you will get this direct runoff hydrograph. This I will come later on. So let it be. Now another issue I have to discuss here. As per the straight line method of base flow separation, we can identify, or we can assume, or we can approximate the position of ending point of a hydrograph. That means what is the point at which this runoff hydrograph is ending, finishing. So it is said that if P is the peak represented by the A point and B is the end of the hydrograph, then the duration from P to B can be given by N, big N, which is empirically assumed to be 0.83, this is a constant, multiplied by the catchment area to the power 0.2. This is the formula. This is an empirical formula, but it is used to approximate the ending point of a hydrograph. Now, if you recall in the first slide, the area of the watershed was given as 27 kilometer square. So, if I multiply 0.83 with 27 to the power 0.2, you can use your calculators to find these values, and you will see that you will get a value of 1.6 days, which can be converted to its hour, 38.5 hours. Okay, and now if you observe the table again, you will see if you add, you will see that at the 12th hour, our hydrograph has attained its peak. That peak is 26 cubic meter per second. If you observe the first, if you observe the table given at the first slide. So from peak to ending of the hydrograph, the peak has been attained at 12 hours, and you are saying or assuming by the baseball separation method that if I multiply 38.5 hours with 12 hours, that means 50.5 hours. That will indicate the ending point of the hydrograph. But again, if you observe our given hydrograph, you will see after 48th hour, 48th hour from the 0 hour, you will see values are either 5 cubic meter per second or less than that. So that is the reason also why I deduct 5 meter cube per second from each of the ordinates, because those flow which are less than 5 cubic meter per hour can be or is occurring due to the base flow only. And that is also the reason why I have taken 48 hours to be the ending point of the hydrograph, not 50.5 hours as indicated by the formula. Because in case of 50.5 hours also, that means the next ordinate is at 54th hour, you see the same value of discharge is given, 5 meter cube per hour. That means at the 48th hour, the discharge is 5 meter cube per second, and also in the 54th hour, the discharge is 5 meter cube per second. And our base flow formula is given that your end is at, or the end of the hydrograph is at 50.5 hours. So as there is no change between 48 and 54, I am taking 48th hour as the ending point, and naturally the 0th hour will be the beginning point. So the entire hydrograph is of a duration of 48 hours. And from peak to end, I have already said that peak is at 12 hours. So the duration is 48 minus 12 equals to 36 hours. So within 36 hour actually the hydrograph has finished or recessed, and this is from the peak value. But our base flow formula is given 38.5 hours as the duration from peak to finish of the or ending of the hydrograph. But as per our practical assumption, we can easily see that within 36 hours, the contribution of runoff or contribution of rainfall to generate this hydrograph has receded. Only the base flow was going on, but base flow we have already deducted. Okay, so now my next step will be to find the area under the DRH. That means this is our area under the DRH. Now you can see from the incremental area calculation formula, we can divide this hydrograph into multiple number of polygons. Okay, and it would be near just like trapezoids or rhombus. Okay, so if you see, if this is the 0th hour, okay, and this indicates the 6th hour, this indicates the 12th hour, this indicates the 18th hour, and so on. So for the first thing, for the first area, this is more or less a rectangle. You see, as this is the beginning point of the hydrograph, and I have already deducted the base flow from here, 5 cubic meter per second is already deducted. So this is basically 0 cubic meter, and this is actually this point or the discharge at 6th hour is originally given as 13 cubic meter per second, but when you deduct 5 cubic meter per second from it, it will give you 8 cubic meter per second. And as per the formula of rhombus, to calculate the area of a rhombus, it is half side 1 plus side 2. Correct? Now side 1 is already 0, side 2 is 8. So it becomes half into 8. Similarly, if I take the next polygon, this is the S1, this is S1, and this is S2. So it is becoming half. S1 is at 6th hour, S2 is at 12th hour. The value of discharge was 13 cubic meter per second at 6th hour. Observe the table is given at the first slide. We have already deducted 5 cubic meter due to base flow. So we have 8 here, 8 cubic meter per second, and this value at 12th hour duration was given as 26 cubic meter per second minus 5 cubic meter per second become 21. So the area of the rhombus will be half 8 side 1, 12 side 2, sorry 21, not 12, 21 side 2, that means 29 half multiplied by 29. Again you take the next case, 12th hour duration, discharge given is was 26 cubic meter per second. You deduct minus 5, it becomes 21 cubic meter per second. Now the discharge given at 18th hour duration is 21. Okay, Now again you deduct minus 5 from it. It becomes 16 cubic meter per second. So the formula is half S1. Now S1 is 21. S2 is 16. Right? This is S2. Right? So 21 plus 16, it is how much? 37 divided by 2. So 18.5. So in the same way, from the 0th coordinate representing the discharge of at 0th hour until 48th hour, because we have found that the end of hydrograph is at 48th hour, for all this incremental area represented by the formula of rhombus, you have to calculate the area and add each of them with the others. That means if first incremental area is A1, then A2, A3, A4, up to so on. So you will add A1 plus A2 plus A3 plus A4 plus A5 and so on. Okay, this is the technique to find the total area under this DRH, direct runoff hydrograph. Now you have found out the total area under this DRH. So A DRH is already you have found out 1, and this, remember, this is in meter cube. Suddenly this will be in meter cube per second. Now oh no, sorry, this will not be in meter cube per second. This will be in what? So this will be in meter square, because this is an area, so this will be in meter square. So you multiply that 3600 that you have done at step 2, first step 2, and you will get this value in meter cube, and this value will be 1.4904 into 10 to the power 6 meter cube. This will be your total direct runoff due to the storm. Now again I am saying that you will ask how I have got this as meter cube. This is a question that you can raise, and yeah, this is a question you have raised, and I have shown you that how to calculate the area of DRH. So in case of area of DRH, when you are multiplying the 6 hour, let it recapitulate a little bit. When you are multiplying 6 hour into 60 into 60, you are getting 3600 second. And when you are calculating the area, although area, the unit of area is meter square or square meter, but what happens is in these cases all the ordinates are represented by meter cube by second. All these values, these 5 meter cube per second, 13 meter cube per second, 26 meter cube per second, all these are meter cube per second. So this term, when you calculate the area, this area under DRH will have a unit of this meter cube per second. And when you multiply this 3600 second with the area under DRH, which has a unit of meter cube per second, so both of these second will deduct it out, and only meter cube will remain. So ultimately, after multiplying 3600 with the area of DRH, you will get area of DRH in terms of meter cube. Why? Because all the ordinates of this area or graph was in terms of meter cube per second. So you have actually deducted meter cube per second from meter cube per second only while finding out the length of the sides. Okay, so the unit was not changed. Okay, even if we have divided by 2, but 2 was unitless. So that is why the area, resultant area has come as per the unit of the ordinates. Okay, so it is generally meter cube per second. And then the moment you multiply 3600 second with this area represented by meter cube per second, the second deducts out, only meter cube remains. So that is why this is the reason why the unit of the area of under DRH is represented by meter cube, not by meter square. Now, so you have got your area of DRH, correct, or total direct runoff. Now this is in meter cube. So what we'll do to come into to get meter, because our aim is to represent all these terms in depth, because we have rainfall at a depth term. So what we'll do, we'll divide this area of DRH represented by meter cube by the catchment area, which is represented by the kilometer square, but it will be converted into meter square by multiplying that area value with 10 to the power 6. So this becomes meter square. Now meter square deduced out and you get your depth. And this depth is known as runoff depth in meters. You understood? Area under DRH represented by meter cube. Catchment area represented by meter square. Meter square deducted out, only 1 meter remains. So runoff depth becomes in meter. So this runoff depth will ultimately comes to 5.52 centimeter, because all this rainfall terms is given in centimeter. So that is why after calculating runoff depth in meter, you have to convert them into centimeter. Okay, and as you know, if so, as you know that if I multiply area DRH, if I multiply the area of effective rainfall, this I was mentioning from the very beginning, that if I multiply area under effective rainfall hyetograph with the catchment area, okay, I will get the area of DRH, direct runoff hydrograph. So if I divide area of catchment from the area of DRH, direct runoff hydrograph, then I will get area of effective rainfall hyetograph, because my main aim is to get the effective rainfall depth. So once I get this area, I am so once I divide the area of DRH, which is in meter cube, by the area of catchment, which is in meter square, I get the area of ERH, or effective rainfall depth in terms of meter. Okay, and this area under ERH, why it is in terms of meter. It is due to the same reason why area of DRH is represented by meter cube. I have already discussed, because all the ordinates of a hyetograph is given in terms of intensity of rainfall, which is generally in meter per hour or centimeter per hour. So this is why this area of ERH will also come as meter or centimeter when you multiply 3600, or if it is in hour, only 6 with this area under ERH term. So what happens is we have the rainfall excess depth. It will come as 5.52 centimeter. Now it is very easy. We already have total rainfall. Let us move to the last slide. Yes. Now as per given data, total rainfall is 3.8 plus 2.8, 6.6 centimeter depth. This I was talking about. Rainfall is given in centimeter. That is why we have taken the runoff depth to also to the centimeter, and also the excess corresponding excess rainfall depth to the centimeter. Now don't confuse between excess rainfall depth and effective rainfall depth. They are basically same. Deduct initial loss and infiltration loss from total rainfall depth, you get the excess rainfall depth. But here I have to find that initial loss only as per the problem. So because phi index is given by the formula total rainfall minus excess rainfall or effective rainfall depth divided by duration of the rainfall, which we have already known from the given data 8. Because we have said each of the storm has been consistent up to 4 hours or existed up to 4 hours. So 4 plus 4, 8 hours. So the denominator is known, 8 hours. Numerator is also known. Total rainfall from the given data, that is 6.6 centimeter. Effective rainfall that we have calculated in the earlier steps and has found that it is 5.52 divided by 8. You will find that this will be your phi index. So there was two questions. What is the value of effective rainfall depth? Yes, 5.52 centimeter. Second question, what is the value of phi index? 0.135 centimeter per hour. So with this, I close this presentation, and we have been successful in solving the first problem of the relationship between DRH and ERH. Thank you, and subscribe and like my video.